Hello guys, welcome to the homework 5 introduction video. This homework is a grade scope assignment out of 2 points. It is unlimited submissions, it's untimed, and you should be able to get instant feedback so you can see whether your answers are correct for the deadline. And it's covering bits and asymptotics. There is an optional skeleton code that goes along with one of the questions on bits, but you don't have to pull the code. It's just a really good way to approach the problem and actually see how cool the thing you're doing is. But you can't submit the code. There is no code submission at all. It's all on Gradescope. I'm actually going to now hand off the mic to Allison of fall 2021 of the past because I already filmed this.
So just to recap really quick, let's talk about numbering systems. And specifically, let's think about the fundamentals of what a decimal number really means, right? You may not have realized it, but you are very familiar with how decimal numbers work, right? We have these 10 digits, 0 through 9. And when we look at a number like this, what's really happening is we see, oh, we've got a 0 in the ones place, right? We've got a 2 in the tens place, a 4 in the hundreds place, and a 1 in the thousands place. And so the way this works out is we see this and we know what we have to do is go, oh, that's 1,000 times 1 plus 100 times 4 plus 2 times 10 plus 1 times 0. In other words, we are adding all this up and we get 1,420 when we add all these terms up. You may not have ever noticed this, but this is the same thing as saying 10 to the 0, because anything to the 0th power is 1, right? And then 10 to the 1, 10 to the 2, 10 to the 3. And so this is really how a decimal number breaks down if you think about it. You probably see these and don't think twice about what this means, but at its core, we are working in base 10, and every spot is basically just 10 to the the nth digit is 10 to the n multiplied by the value there at that of the digit there, right? So this is how a decimal number works. And a binary number is actually totally the same. The only difference is that now we're in base 2. And so base 2 just basically means the only digits are 0 or 1. And unlike before where we were working in multiples of 10 down here, or base 10, we've got 2. And so the binary number 1010, if you wanted to think about it in terms of decimal, is really just going to be the value here multiplied by 1, the value here multiplied by 2, the value here multiplied by 4, and the value here multiplied by 8. In other words, you can think of this as the 1's place, 2's place, 4's place, and 8's place, similarly to how we had 1's place, 10's place, 100's place, 1000's place. And again, if we take these numbers and sort of look at them in terms of 2 to some power, it's 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3, right? Because 2 to the 3 is 8. And so this is just the same as what we had in the decimal case, but we're working in binary. And so digits must be either 0 or 1. And so this is how a binary number works. And again, this is if you wanted to translate this binary number into a decimal number, you could just say, oh, well, it's 1 times 0 plus 2 times 1 plus 4 times 0 plus 8 times 1, or 10. And so this binary number is 10. Note that the bits are actually indexed from right to left. And this makes sense because we're going from the least significant to most significant. And so this is the bits are indexed from right to left. And so this is the 0th bit, the 1st bit, the 2nd bit, and the 3rd bit. This might be a little unintuitive because in English, right, everything goes from left to right. But when we're talking about bits, it actually makes sense to go from least significant to most significant. And a bit is just the smallest unit of data we can talk about, right? It's the smallest unit of memory or computing that really is tangible. And a single binary number takes up 1 bit. It's either 0 or 1, but regardless, the memory or the unit of data it takes to store it, whether it's 0 or 1, is 1 bit. A Java int is 32 bits, for example. A long is 64, a character is 16. And all of these different data types takes a different number of memory to represent or amount of memory, depending on how complex or large they are and how much detail we need. And I want to point out something important, which maybe seems intuitive, maybe not, but keep in mind, it takes as much like storage or memory to store the number 0 is if it's an integer, and to store the integer like, I don't know, 2,432, right? These take up the same amount of memory because at the end of the day, one int must be 32 bits. It just happens to be that for 0, all those 32 bits are like 0, right? And for this, it's much more, or there's more like non-zero bits, but they both take 32 bits to store. And this is because that's just how an int is defined. And we have to sort of keep them uniform. We can't say that like an integer that stores a smaller number is smaller because it would just be a huge mess. So we keep them all the same. And so this is how basically like bits work, right? And we're going to talk a little bit about bit twiddling, which you've already seen in lecture. So even though you might write your code like so, right? Int x equals 1, under the hood, the value stored within x is actually going to be represented as the following sequence of bits, right? 1, and then a bunch of zeros. And so Java provides us with bit twiddling or bitwise operations that let us operate on the underlying bits rather than just the decimal number representation. And so if we wanted to work with x and say, oh, I want to flip all the bits, or I want to change the, I don't know, the second bit to be some other value, Java lets us do that using bit twiddling. And so if you don't recall this slide from lecture, these are the operations that you can use for bit twiddling. And I would really recommend watching the lecture again, honestly, if you're unfamiliar with any of these, but basically mask goes through and says, or it's basically saying and, right? If for every value, if both of them are 1, then I will return 1, right? And so this one, we're going like down like column wise, right? And we say, oh, these two are both 1, it's 1. And here, like they're not both 1, right? And so this is 0. That's how mask works. Set is kind of like or. It's saying if either one of them, at least one of them is 1, I will be 1. And so in this case, the bottom number is 1, so this is a 1. In this case, they're both 0, so it's a 0. And in this case, since either one of them happens to be both is 1, it's a 1, right? So set is saying like as long as one of them is true, it's true. It's similar to the Boolean or. Then we have this flip. You can also think of it as sort of they must be different. And so here 1 0 1's 1, so it's like 1 here. Whereas in both of these columns, they're both the same, right? It's 0 0 and 1 1, so these actually turn out as 0. And so flip is looking for difference. And then flip all, or this like little tilde, basically it only works on a single number, and it's just gonna like negate every bit or give the opposite of what was there. We can also shift, and so you specify like the amount you want to shift by, right? And so here, if you shifted by 3, you're bringing in 3 zeros and pulling everything. Like you can recognize this sequence is the same as that sequence.
And for the right shifts, there is both the arithmetic right shift and the logical right shift. And so you might be wondering why we have 2, but the idea is that, recall, in a 2's complement representation, right, the leftmost bit is the sign bit because the leftmost bit lets us know for negative. And if you're unfamiliar with this, I would recommend, rewatch the lecture, but basically the idea is that the leftmost bit in a 2's complement number carries negative weight, right? And so if this was an 8-bit number, for example, so this is the whole number, it's not an integer, which is 32, right? Then this is our sign bit. And so with an arithmetic right shift, if we shift right by 3, we're going to bring in a copy of the sign bit. In this case, it's a 1. So we bring in 3 1s, and then the rest of the number is shifted down, right? If, in this case, this bit was a 0, or the sign bit was a 0, we would have brought in 3 zeros. So the key thing is that with an arithmetic right shift, we're preserving the side of our number, which is why this is the arithmetic right? Or the arithmetic shift, because we are doing what like mathematically makes more sense by preserving the sign of the number. The logical right shift, however, always brings in zeros no matter what. So even though we have a 1 in our sign bit for this 8-bit number, we're still bringing in zeros. Now I'm going to talk a little bit just about the grade scopes assignment so you can have like an idea of what you're stepping into. Question 1 is just sort of a warm-up question in converting between decimal and 2's complement binary numbers. This is a good way to make sure that you're ready to move on to the rest of the assignment because this is sort of like our bread and butter, the fundamentals. Then we're going to do some basic bit twiddling operations. So this is your shifts and your and, or, XOR, flip, whatever. And so these are just practicing those bit operations. And once you're able to understand the bit operations, now we can actually move on to some of the more challenging exercises that ask you to help complete functions. And so my recommended approach is that, all of these, we tell you like, how do you find all the numbers that are a power of 2? And so, for example, what I would do is try each option with an example number and see which ones work and which ones don't. For example, with the power of 2 question, I would try it with a number like 16, which is a power of 2, and make sure that it says, oh yes, this is true. And then try it with a number like, I don't know, 9, which is not a power of 2, and make sure that one is false. And so try each option that we give you, because it's multiple choice, with an example, and then narrow it down to the ones that work. And then once you've narrowed it down to maybe, let's say, like 2 answers that you think, oh, both of these could be reasonable, just like think about more cases and work based off that. But I think with the exercises, it's just really valuable to use examples. And finally, nibbles. And so again, I'm gonna give it away to Pass Allison to talk about this.
And so here our goal with this task is we want to store an array of nibbles or 4-bit numbers. So a nibble just means 4-bit. This is much smaller than the primitive number types we're used to working with, right? For example, one of the primitives we know very well is int, that's 32 bits. Even the smallest number type that Java supports is a byte, which is 8 bits. And so that's too many for what we want, right? So the question is, how can we store an array of nibbles when Java doesn't actually have a primitive nibble data type? So I encourage you to pause the video real quick, think about it maybe, and we can come up with our first sort of naive idea. So we'll just say, oh, we'll just use like an integer array or something, and we'll fill all the unused space with zeros. So for example, if we wanted to store the nibbles 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, and 0, 0, 0, 1, we could do the following in an int array. And so we would just put the nibble as the least significant bit of the int, fill the rest with zeros, and then put this in an int array. And so notice this is one 32-bit int here, another 32-bit here, and we have basically 4 ints in this int array, right? And the nibble that we want is just going to be the 4 least significant bytes or bits. Sorry, I keep saying bytes, I mean bit. And so maybe we see a problem with this, which is that we are being very wasteful. And, we really believe in this zero waste 2020. I guess it's 2021 now. We believe in, not being wasteful, right? And so how can we make this more efficient, right? We're spending all this space on just storing zeros. And so you realize we can just pack the nibbles in. All 4 of these nibbles can actually fit into one integer, right? We can put them in right here. And in fact, we can fit 8 nibbles in an integer, right? We have even more extra space. This makes sense because an int is 32 bits, a nibble is 4 bits, and so 32 divided by 4 is 8. So we can fit 4 nibbles in one int. Or in other words, if our int array is of length n, then we can actually store within there n times 8 nibbles, right? An int array with n ints can be n times 8 nibbles. And so a user of the nibbles class might say, oh, hey, I have these awesome 16 nibbles. I'm going to put them in an array. And to the user, they can say, oh, can I get the 0th nibble? Can I get the first nibble? Can I get the second, whatever? Can I get the, sorry. Okay, and so the user will say, can I get the 8th nibble? And you, as the programmer, are actually under the hood going or I guess it's not you as the programmer, but the code you write as the program will go and say, oh, sure, I'll get you that 8th nibble. It's right here. And if you say, can I get the 0th nibble? You go, ah, sure, it's right here. And so the user has this abstraction or this view of the data as this like regular old array with regular old indices. But what you're actually doing is you are putting these nibbles into an integer array where 8 nibbles can fit in one integer. And so to store a 16 nibble array, all you need is 16 divided by 2, or sorry, 16 divided by 8, or length 2 int array, right? And so I want to point out something really important, which is that notice how within the block or within one integer, we are going from right to left because the 0th nibble or the like least significant nibble should go at the 0th or least significant nibble within the int, right? And so like we said earlier, when we are talking about like within a number, the least significant is the thing to the right. And so here the 0th nibble is the thing to the right. The first nibble is going to be second to the right, right? And that corresponds to this. And so we have this correspondence. And if the user were to say, can I get the 8th or 9th nibble? You would have to go, oh, sure. Well, the 8th nibble is actually going to be in index 1 and oh, it's right here. And the 9th is here, etc. And so you have this underlying int array named data, and you have to figure out how can I be smart and operate on the bits within to get the correct bits for whatever the user selects. And so this will require you to use those bit twiddling operations we talked about earlier. I do want to point out that it's easier to sort of think about things in sort of these like groups of 4 binary numbers, right? At least for me, that's how I like to think about it. But maybe you, for whatever reason, like to convert all of these into like decimal, and you can think about it that way. Or we can even point out that this altogether, if you were to like look at it in the debugger or like just look at the number, this binary number actually corresponds to this and this decimal number. And that's using that same like method of translation we found earlier, right? You're just going through and adding all the values appropriately. Or more realistically, you look up online binary to decimal converter and you can get those. But I just want to point out that like this is how it might actually look. But what you are really working with deep down are these bits, and that's what you want to be operating on.
Thank you, Pastor, for talking about nibbles. So basically, nibbles on the Gradescope assignment, you can, fill in the like multiple choice and try to complete the methods to do what we've described in nibbles. But if you would like, you can pull that skeleton code and work on nibbles as a coding assignment and sort of do it more hands-on. And that might be, for some of you more fulfilling or easier to understand. But question 5 on the Gradescope assignment, it's very challenging. I don't even want to talk about it. You'll see how hard it is when you get there. It's not hard. It's a picture of a dog. It's not my dog. I wish it was. And question 6 and 7 are asymptotic analysis. And so these are some practice bounding functions. And if you are stuck on how to do questions 6 and 7, I think actually the best thing to do would be to attend discussion or watch the discussion walkthrough videos, because I think those are a more thorough like sort of practice for asymptotics. But that is homework 5. Have a great rest of your day. Yeah, enjoy the sunshine.